evening. Welcome to yet another lecture of the Applied Analytics course, where we are looking at a practitioner's approach to descriptive, prescriptive and predictive analytics. And we have already seen the philosophy behind analytics, how is it different from data mining, and the certain aspects of how do we look at the data, describing the data and all those kind of stuff. And today we are going to deal with a new tool which is known as the box plots. And the box plots is a tool. This is a descriptive analytics tool that is versatile. Versatile means it can be used for many other things, and we will see the versatility of this tool in the lectures after this. So, let us talk about some of the fundamental concepts before starting with the box plots. And first let us talk about median and quartiles. So, we all know that there is multiple ways to measure there is measures of location and measures of variation. We already discussed this in earlier, but location is sometimes, like for example, is measure of central tendency, which means where is the center of the data located. Okay. So, couple examples will be like mean, median, they are all that examples. Okay. They are all part of the central tendency. And measure of variation, we know that how much variability in the data, how much variability in the data, and some example is variance, range, standard deviation, etc. Okay. So, one such case of the measured central tendency is the median. Okay. And let us say what is a median? A median, it is a descriptive measure. It is a descriptive measure of center of the set of data. Okay. We are trying to measure the center of the set of the data, or it is also as a central tendency, but it is in a way median is the middle value, which implies it divides data set into two equal parts. Okay. Now, the obvious question is, how is median calculated? Okay. We have not seen this in the class, so we will quickly see how it is done. The first thing to do it is sort. So, how is the median calculated? Sort data in the ascending order. Okay. Ascending order means lowest to highest. Then second step, identify the number of data points. The number of data points, okay, usually denoted by lowercase n, small n, if n is an odd number. What we are saying here is, if the n is an odd number, then median is the value, of the n plus 1 by 2th observation. Okay. If you find how many data points are there in the data set, and if the value of n is odd, if it is an odd number, okay, it is not divisible by 2, then the median is the value of the n plus 1 by 2th observation. Okay. If n is an even number, it can only be odd or an even. Okay. So, if it is an even number, then what do we do? Then median, okay, lies between the value of n by 2th observation and n plus 2 by 2th observation. Okay. Then find the average of the values of both these observations. So, if it is if n is odd, if it is an odd number, you find the n plus 1 by 2th observation and the value of that will give you the median. If n is an even number, then the median will lie between n plus 2th observation and n plus 2 by 2th observation, and the average of these two values, whatever the values that you get, that is what is called as the median. So, the median is denoted by, okay, it is also denoted by x tilde, okay. Tilde is the squiggly thing, okay. Mean, on the other hand, mean is denoted by x bar, the line on the top, okay. This is the tilde, this thing, okay, the curvy thing. All right. So, let us look into an example, okay, quick example. So, let us take a data set 1, okay. The first data sets, let us talk about it as 15, 14, 2, 27 and 13, okay. And the data set 2, let us talk about the second data set as 11, 9, 17, 19, 4 and 15, okay. So, let us start with the data set 1. So, set 1, the first step is step 1, sort the data. So, the sorting will give us, it will be giving us 2, then it will give us 13, then it is 14, then 15 and 27, okay, fine. So, the value of n equal to 1, 2, 3, 4, 5 equal to 5, which is an odd number, okay. So, the rule is x tilde is the n plus 1 by 2th observation, okay, which implies 5 plus 1 by 2th, which implies 6 by 2th, which implies the third observation, okay. So, which is the third observation? Third observation, the sorted order is 1, 2, 3. So, 14 is the third observation. This implies x tilde, the median is 14, okay. The value of median is 14, which is the value of the third observation in the sorted data, okay. You have to remember that the data has to be sorted no matter what, fine. So, now similar, let us look at the set 2. Step again, first one, sort the data. So, sorting gives us, we start with the sorting, it is 4, 9, 11, 15, 17 and 19, okay. So, the value of n equal to 1, 2, 3, 4, 5, 6, n equal to 6, which is an even number. Okay. So, this is a number that is divisible by 2, it is an even number. So, then what do we do? So, then median lies between n by 2th observations value and n plus 2 by 2th observations value. Okay. So, what is the n by 2th observation? N by 2th implies it is 6 by 2 implies 3. So, it is a third observation, okay, value, which is 1, 2, 3, 11, right. Okay. Now, observations value, then n plus 2 by 2th observation implies 6 plus 2 by 2 implies 8 by 2 or the fourth observations value. Okay. And this values both come from the sorted order, that is 1, 2, 3, 4, that is 15. Okay. So, now median x tilde is equal to the midpoint of this, okay, 11 plus 15 divided by 2, which is equal to 13. Okay. So, the value 13, which is between these. Okay. So, if you look at it here, you can see that it is 2, 13 is one set and the other one is 15 and 27 and 14 becomes the median. So, it divides the data into two equal parts. If you think at it, there are two values here and two values here. Similarly, if you look at this case, you can see that the values 4, 9, 11, then you have 15, 17 and 19 and you have 13 in between, okay, which is your median, which divides the data into two equal parts. You can see that the 11 up to 4 to 11 is one part, this is the other part. Okay. So, this is the simplest way how the data, the median is calculated. Okay. Now, once you know how to calculate the median, we can do many more fancy things out of this. So, first thing to do, let us say, is that let us talk about the concepts of quartile, okay, quartiles. So, when the data is ordered, okay, when the ordered data set is divided into quartiles or quarters, then the resulting division points are called as quartiles. Okay. So, if you think about data as x1, x2, x3, x4, etc. up to xn, and if you divide them into quarters, okay, if you think about it as the first one x1 to some number will give you the first quarter, then from here to median x tilde is the second quarter, then the third one is the another set of data and then the last one above this. So, if you divide this into quarters, this is the middle point, the 50th percentage, this is the 25th percentile and this is the 75th percentile. Okay. So, these kind of points, these percentile points are typically what are called as the quartiles. So, the first one we are going to study is the first quartile or what we call as the Q1. The first quartile Q1 is a value that has 1/4 or 25% of the observations below its value, right. Similarly, if you talk about it, Q3, it is a value that has 3/4 or 75% of the observations below its value. Okay. Another way to think about it is, or 25% of the observations above it. Okay. Here you can think about it as, or 75% of the observations above it. So, as I said here, when you think about the 25th percentile, this side of it will contain the 1/4 of the data, and this will be the 3/4 of the data. If you think about the 75th percentile, this will be the 3/4 of the data, and this will be the 1/4 of the data. Okay. So, unlike median, which is exactly a middle point, Q1 and Q3 might not uniquely define a percentile. That means it need not be exactly in the middle of two observations. Okay. Because at some point of time, more than one observations can satisfy the definition. Then if that happens, then we take the mean of both the observations. Here the mean of both observations, okay, are taken. So, let us talk about this general definition of percentiles. Okay. So, we will talk about in the next slide. So, let us say before we get into this example, let us talk about the definition of the percentile. Percentile definition, how do we define this? Okay. The definition of the percentile. The sample 100 times pth percentile is a value, okay, such that at least 100 times p percentage, 100 p percentage of the observations are at or below this value and at least 100 times 1 minus p percentage are at or above this value. So, if you look at this, the definition says the 100 pth percentile of a value is a value such that at least 100 p of the observations, 100 p percentage of the observations are at or below this value, and at least 100 times 1 minus p percentage observations are at or above this value. So, if you think about it, the previous case is exactly what I was talking about. The 25th percentile means 25% of the observations are below, at or below this value, or 75 percentages. So, this is the 100 p percentage, this is the 100 times 1 minus p percentage, okay, that is above the value. Similarly, this is in our case is the 100 p percentage, and this is the 100 times 1 minus p percentage in the case of the 75th percentile. Here is the 3/4 and the 1/4. Okay. So, let us do an example, and usually doing an example usually helps us to understand how things are. So, this is our time to have lunch data, and the credit of this data goes to Stephen Terrell's statistics translated book. So, we will use this data to demonstrate or illustrate these examples. So, first is number of observations. Okay. That is n, which is 12 times 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and there are 3. So, the 12 columns and 3 rows, there are 36 data values. And this is anyway in sorted, okay. This is already sorted data. So, the first step is already given to you, sorted. There are 36 values. So, now since n is even, Okay. X tilde is the mean of n by 2th and n plus 2 by 2th observations average, which is equal to the n is 36. So, it is the 36 by 2 2th observations value and 36 plus 2 by 2th observations values average, which is 36 by 2 is 18, 18th and 19th observations average is what we need to take. So, that is the first row is 12, then 13, 14, 15, 16, 17, 18. So, this is 18th observation. This is also the other one, the 19th observation. So, the median can be calculated as 55 plus 55 by 2, which is equal to 55. Okay. So, the median comes to be 55 and both the values are identical. So, the median will also be 55. So, what we are saying here is the value here, somewhere here exactly, will split the data. The number of data points below this is the 50 percentage of the data and the values above this is the other 50 percentage of the data. That is why it is the median. So, now similarly, let us do Q1. Okay. Q1 is the 25th percentile. So, which is 0.25 times 36, which is 9, which is 1/4 of the 36. 9 implies find a value that will have 9 at or below it, or 27 observations, because there are 36 of them, the remaining 26 observations above it. Okay. In this case, if you think about it, you can think about it as 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the 9th observation, you can think about it, and it will have 9 of them, and above this will have 27 of them. Or if you take this 10th observation also, you can find that from starting from here, it will have 9 below and it will also have the 27 above it, at 10 above. Okay. So, these 2 points will actually work in our case. So, then the 9th observation is 9th value is equal to 45. Then similarly 10th value is also 45. So, x 0.25 or the Q1 first quartile is equal to 45 plus 45 by 2, which will be 45. In software packages, typically software packages like R and all, it will act, if these values, let us say instead of 45 and this one, this was 45 and 50, if that was the case, then it would actually extrapolate it between it correctly, but in our case we will just take the average of that, if that was the case. Okay. Similarly, let us calculate Q3. Okay. The Q3 is the 75th percentile, 0.75 times 36 or 3 by 4 times 36, which gives us the value of 27. Okay. This implies that there should be at least 27 observations below it or 9 observations above it. Okay. So, if you look at it, the candidates are, this is 12, another 12, 24, 25, 26, 27. So, this is one point where the number of observations below this are 27, including this, or it could think about here this 28th observation, on which including this one we have 9 observations above it. So, we have 2 candidates, okay, which implies there are 2 candidates. So, in that, if you think about it, what we are going to do now is both 27th and 28th observations satisfy the definition of the percentile. So, what do we do? The 27th observation is, as I said, it's 65. Okay. 27th observation is the 65, value is 65. 28th observation, the value of the same is also 65. Okay. So, the Q3 x 0.75, the 75th percentile value, or Q3 is 65 plus 65 by 2, we find the average of it, which is 65 again, right. So, we have now the Q1, we calculated it as, from the previous slide, we calculate the value of Q1 as 45. Okay. Q2, which is your tilde, the median, was calculated as, we calculate the median as 55. Okay. And Q3, the 75th percentile, is calculated as 65. So, we have 3 of these values that we calculated. Now, before getting into this, let us take a scenario where we make this as a graph. Okay. So, let us take the x axis like a long number scale. Let's start from here as 0, 10, 20, 30, 40, 50, 60, 70, 80, like this, the number goes, and this side you have minus 10, minus 20, like this. And if we find out what is the Q1 in this number scale, Q1 is 45, so it is somewhere here. So, this is your Q1. Okay. So, this is Q1 45, and the Q2, the median is 55. So, we will draw another line here, 55, the Q2, and the third one is your Q3, which is 65. So, we will draw another line here, which is Q3, and if we connect all of them together with a rectangle, this is called as the box, okay, or the box plot. So, box plot is the graphical representation of the quartile information. We will see the definitions later. Okay. And so, if we go back to the slide, the graphical display that represents the summary information contained in the quartiles is called as the box plot. Okay. So, when we talk about this, whatever the summary information contained in the quartiles, how are they, is clearly defined by box plot. Assume that in a scale like this, you had, instead of this, assume that the values happen to be 40 and 59 and 62. So, then the box would be something like 40 here, 59 will be close to 60, and the other one is 62, which will be close here, and you will have a box like this. Okay. So, here you can see that it is a symmetric box plot, because it is symmetric about the median. This is equidistant, okay, equal. Here this is not symmetric, it is asymmetric. Okay. So, this is an asymmetric box. So, it tells you how the data is distributed with respect to the median, and this is your median, right, median, this is our median or the middle value. Here you can see that the data has a skew, a large spread below median. Okay. So, this is an important information, or the spread above the median is also small. So, that kind of a thing. Okay. And obviously, the second part is, it is a very effective in graphically portraying comparisons among different set of observations. So, if you assume that these two are two different box plots, then we can easily compare them, because we know that the Q3 of the first box plot is lesser than the Q3 of this and stuff like that, and the Q1 is also less, the median is this, there is a spread. All these patterns are clearly demonstratable using this box plot. Then box plot can also be used for identifying potential outliers. So, before completing this, before we getting into the outlier business, let us find out which are the smallest values of box plots, or the smallest and the largest values. So, if we go back to the data, the smallest value is 30 and the largest value is 80. Okay. So, we come here, the smallest is 30, largest is 80. So, if you take here, here is 30, you draw a point, and here is 80, you draw a point and you connect them with the box. Okay. This is typically called as the whiskers. Okay. So, hence this is also called as, hence it is also called as box and whisker plot. Okay. When you connect the smallest and the largest values with the box, then it becomes the box and whisker plot. So, this is only box. Okay. This is box and whisker, this one is box and whisker, you can see that the bottom one is the box and whisker plot. Okay. Now, with this, armed with this, we can also say that the box plot is also a good tool for identifying potential outliers. So, outliers are, so one we will see what outliers are later, very clear definition, but outliers are data values that are too distant from the rest of the data. Okay. So, that is what we call as the outliers, and box plot is a good technique. Box plot can be enhanced. Okay. If you add the fencing technique onto the box plot, then you can use it to identify the outliers in the data, or the potential outliers in the data. There are 4 type of fences in this. Number 1 is our lower outer fence, typically called as the LOF. Number 2 is the lower inner fence, typically called as the LIF. The third one is called as the UIF, upper inner fence, and the fourth one is called as the upper outer fence, called as the UIF. So, we create all these fences onto the box plot, and from using that we try to identify the outliers. So, let us see how to make the fences. Okay. So, the first thing before making the fences we need to understand is define a concept called interquartile range. Okay. So, remember in our previous example we had the Q1 as 45 and Q3 as 65. So, using that we can identify what is called as a topic called interquartile range, typically known as IQR, okay, defined as the difference between Q3 and Q1. So, IQR in our case is equal to Q3 minus Q1, which is pretty much 65 minus 45, which is equal to 20. Okay. So, this is called as the interquartile range. So, what is the range of the data? Range of data is equal to max value minus minimum value, which is 80 minus 30, which is 50. So, the IQR is the range between the Q3 and Q1, whereas the data range is between the min and the max value. So, the fences, okay, fences are created using IQR, okay, equations, IQR and the following equations. Okay. What are those equations? Upper, let us start with the lower fences to make our life easy. We will start with the lower inner fence, okay, or LIF. This is given by Q1, the quartile, the first quartile 1 value, Q1 minus 1.5 times IQR, that is your lower inner fence. So, upper inner fence will then be symmetric. On the other side, UIF will be, it will not be Q1, it will be Q3 plus 1.5 times IQR. That will be your upper inner fence. Okay. And the now let us talk about the outer fences. Lower outer fence, the LOF is equal to Q1 minus 3 times IQR, and upper outer fence that is UOF is equal to Q3 plus 3 times IQR. Okay. So, if you visualize this, in this case you already know what is the values of Q1 and Q3. So, in our case if we calculate it, we can get it the LIF is equal to Q1, the value of Q1 is 45 and that is minus 1.5 times IQR, we calculate the value as 20. So, it is 45 minus that will come to 20, 20 half 30. So, that will be equal to, you get the value of 15. Okay. Then similarly upper inner fence, let us talk about the lower outer fence first. Lower outer fence will be again Q1 minus 3 times IQR, which is equal to 45 minus 3 times 20, okay, which will give us the value as minus 15. Okay. Similarly, the upper inner fence is equal to Q3 plus 1.5 times IQR, which is equal to, for it will be what was up 65 plus 1.5 times 20, okay, which will give us 95, and the upper outer fence is equal to Q3 plus 3 times IQR, which is equal to 65 plus 3 times 20, which will give you 125. Okay. So, these are the fence values that we get. Using these fences, we can embellish the box plot. Okay. So, we will see how to do that. So, as we did earlier, we will draw the line again, okay, just to remind you how to draw the box plot once again. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. Let us assume it this way, and here we have minus 10, minus 20 like this, and the starting value of the fence was 45. So, we start with the Q1 45, Q2 as 55 and Q3 as 65, all the 3 values drawn like this, and the minimum value was 30, maximum value was 80. They are connected to the box, which gives the box and whisker plot. Okay. This is how you are drawing the box plot. Now, the question is the fences. So, the first value of the fence is at 15. So, 10, 15. So, this is where the lower inner fence will come into picture, and the upper inner fence was at the value of, as we seen earlier, was at the value of 95. So, we come to 90 and 95. This is where the upper inner fence will come into picture. Now, we see what are the lower outer fence. The lower outer fence was minus 15. So, if you go to the diagram, we will find minus 10, minus 15 will be right here. So, it will be the lower outer fence, and similarly if you look into it, we find out that the upper outer fence is at the value of 125. So, we come here at 120, 125, and this is our upper outer fence. Okay. So, the trick here is that using these fences, okay, you can find out the outliers. The idea is this: all values between the rules, okay, the rules are this: all values between inner and outer fences are potential outliers. Okay. So, this area, this is a potential outlier. Okay. This is another potential outlier. Okay. Then all values below and above outer fences are usually outliers. Okay. So, this area and this area, these are outliers. So, the values between these inner fences are supposed to be belonging to the same data set. So, as long as the values are lying between these inner fences, you can call it as they are kind of behaving like the other data points, but the values between the inner and the outer fences typically become what we call as the potential outliers, and the values outside the outer fences, okay, below the lower outer fence and above the upper outer fence becomes outliers, okay, designated outliers. So, box plot demonstrates the data spread and also allows to identify outlier data. Okay. So, this is one good advantage of the box plot. Then obviously, if you are doing box plot, then one question is, when you have a large data set, it is very hard to do box plots with your by hand. So, you would require a software, and in this case the particular software that we are creating here is the using, as we said, this class we will be using R. Box plots are extremely easy to do with R compared to Excel, and the command that you need to learn to do it is the box plot function. So, it is basically box plot. So, what you need to do is, first you need to set up a vector of numbers and then use box plot command to plot the same. So, first you set up the numbers and then you use the command, and the command also has a lot of options which you can learn and find out how, which allows you to make quite a lot of different complicated type of box plots. But the simple code is like this: if you give a data set, this is the creating the data set. Okay. So, you create a vector A with it is a set of 12, 30, 30, 30, 35 these kind of values, and then you ask it to, here is what you are doing, creating the box plot. Okay. So, when you use this box plot command and feed the data value, the R software will then do the box plot for you, and you can add the fences and all other aspects to the box plot by manipulating this box plot command. So, to find out the details of this, please refer R manual. Okay. But to make a box plot in R with a large data set is very simple, it is just 2 lines of code. Okay. With that, we come to the conclusion of the box plot descriptive analytic tool today, and in the next sessions we will now start with the some aspects of what is data warehousing, what is business intelligence, what is data mart, and that kind of concepts, and then we will start with the normal distributions, after which we will move towards hypothesis testing, which is the fundamental cornerstone of data analytics. Thank you for your patient listening, and we will see you soon. Thank you.